Alrighty. Well, we are live on the air on Google Hangout right now, and so we're covering topic 15, chapter 4, electrons going with the flow. Now, I had over here on my other screen, and these things I have them up on the Dropbox. Some of this. These are some of the symbols. Dave, you're probably more familiar with these. I don't know how you are, John, with some of this stuff, and I'm going to kind of get this and kind of zoom in a little bit. These are more schematic symbols. If you were looking at a schematic, you would see this kind of information on there. But these particular symbols are actually representation of physical components like this here. And you have resistors and diodes and transistors and LEDs, capacitors, and all other sorts of them. And that's what these kind of represent. Now, there's a little more here as far as the schematic is concerned. The schematic symbols are concerned that aren't actually in this reference sheet here. This information is up in Dropbox, like I said, and you all should have the link to that. But I can just point out here that there's in this area here, if you can see my little thing, that's symbols for LEDs or diodes, and that's what an LED looks like. There's a diode here. That's a symbol for a diode, and these are also marked with some symbols on them as well. The transistors have uh, designations on their legs, and we'll get into that as well. But it shouldn't let this stuff intimidate you or frighten you. It's pretty basic stuff. And I'm going to go ahead and go back over and we'll get started with the topic here. I got some other things to share here in a little bit as well. Where's my? Oh, there it is. I got to bring that over here and minimize some other windows for a moment. And here we go. So if you've kind of looked at some of this, and this starts on page, what is it, 153? No. Starts on page 139, and we're going to try to identify some of the nuances, the relationship between voltage and amps and resistance and capacitance and inductance. And some of these have some similarities, but different functions. So, anyway, uh, the electrical term for electromotive force or EMF that causes electrons to flow is, if anybody knows that, okay, very good. Yes, that is correct. It is voltage. So you think of voltage as water pressure in your kitchen plumbing. So you open the valve, you turn on the switch, and current begins to flow. The pressure is voltage, and the trickle of water is similar to current. And so it's the force or the power behind the current or the flow of electrons. And I'm going to use those interchangeably because that's predominantly what the flow of electrons are, is current, and it's measured in amps. And we'll learn that here as we go on. But voltage, so if you have a 12-volt battery, um, there's 12 volts pushing whatever amperage is needed to start your car or to run devices on your car. If you have 110 volts in your house, when you plug in your lamp, you have 110 volts pushing that current to your light bulb. And that's what that's how they design everything. Is it's either AC. We're going to get into AC and DC and understanding the difference between those as well. Okay. So the unit of electromotive force is, and I think I covered this before, is the volt. And another name for voltage is electromotive force or EMF. A little play there on Star Wars. May the force be with you. At any rate, volt just stands to reason that voltage is measured in volts, or EMF is measured in voltage or volts. Which instrument would you use to measure electric potential or EMF or voltage? What kind of meter would you use? In this case, your answer would be B. You're measuring voltage. It only makes sense that you would use a voltmeter. And right now, I'm going to. Hams usually have, you know, a little bit of test equipment hanging around in their shack, and it doesn't have to be expensive or anything. I'm going to stop sharing just for a minute, and I'm going to show you a little meter here. This little meter is not very expensive. I bought this at Harbor Freight, and it's a good little meter. It has various functions, but it's also called a multimeter. So with this meter, I can measure voltage, I can measure current, and the voltage can be either DC voltage or alternating current, DC uh, uh, AC voltage, basically alternating current or direct current. Depending on where I select it, I can also measure amps. I can measure resistance of a resistor, and it also allows me to test um, transistors. There's a little place here where I could plug in a transistor and test it to see if it's functioning properly if I wanted to. Kind of like, the old days tube tester. You'd take a tube out of your TV and run it down to the local drugstore or whatever and test your tube or whatever. But this is relatively inexpensive. It's a little cheap one. And I kind of bought this one predominantly to travel with. I do have a more expensive one here. It's a Fluke 75. I've had this for a number of years, and I'm just going to hold that up real quick. And it has, a little bit different front end there. It's a digital readout, and I can select my. Let me get up here a little bit, stand up, because this is the off position. It saves the battery. There are batteries inside these meters that need to be replaced once in a while. So I have AC voltage here. I have a DC voltage. I can do some, I guess that's millivolts if I want to get down. If it's real small voltage, I can measure ohms. This can tell me if there's continuity in a line. There's amperes. This is AC amps. This is DC amps. And it's got a couple other plugins here that I can use for other functions as well. And this meter is a little bit more expensive, and every once in a while I misplace it and I go, no, I can't misplace it. I love that meter. I got to keep it handy. But I usually end up using this one. It is very compact and very lightweight. So what does it cost? Like what, the little the red one? The red one is available at they say you can get that at Harbor Freight for like $10, 10 or $12. I can't remember exactly how much I paid for it. My Fluke, however, a little bit more higher end meter, I probably paid, I can't remember, 75 to $100 for it. And of course, a lot of these prices have come down quite a bit.
The red one from Harbor Freight, every so often, if you watch their coupons, it's one of their freebie items. But I have the red one. I got it as a freebie item from there.
And you know what? I may have gotten it as a freebie item. I don't know. I can't remember. But I think
they're under $10, John.
Yeah, $9.95. And that's all you really need in the shack, so it's not a big deal. All righty. Thanks, Dave. Let's see. Where am I? Get back to my screen share. Present to everyone. So that's what a voltmeter, or actually a multimeter, looks like. Has the ability to measure voltage. All right. What is the correct way to connect a voltmeter to a circuit? And that's very important because it. In essence, you want to connect it in parallel, okay? When you test something. Yeah, B is the answer. We test for voltage by hooking our meter across the voltage source without undoing any wires. It's a parallel connection, and you can check the voltage when operating equipment. It's called checking the voltage source under load. Um, Let me see here. Let me pull something up here real quick. Okay. And there, I just put a little basic circuit up on here, and how you would do this if you wanted to check the voltage of the 9-volt battery, you would put your probes, one probe on this one and another one on that one, depending on which one is negative and which one is positive, and you could tell if whether that battery was actually 9 volts or not. But you wouldn't want to put it in series. Do, 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 do. All right, close that up. Let's see. So your parallel connection is what you really want when you're doing that. Now, which of the following battery types is a rechargeable? There's a lot of different types of rechargeable batteries out there these days. And one of them that's not really rechargeable is an alkaline or even a standard carbon battery, but definitely the nickel metal hydride, the lithium ion, and the lead acid or gel cells. Of course, all those answers are correct. They are rechargeable batteries. A lead acid or a gel cell is kind of like the battery in your car. Lithium battery would be something like in your cell phone. Nickel metal hydride, is just another type. As a matter of fact, let me jump over here real quick. I'll be right back. Let me show you what I have here. So I'll stop sharing. Tom's here now. Hi, Tom.
Good evening.
All right. But this right here is a gel cell right here. Let me turn it around. That's a little gel cell battery, and I've worked a lot with these. These are pretty cool little batteries. They are rechargeable, like it says, and well, actually, this is a sealed lead acid battery. I did have a gel cell around here. I thought this was the gel cell, but gel cells are very similar to this as well, and it is a rechargeable. It's a 12-volt battery, and it is rechargeable. Okay. Let's see. All right, John, you'd asked a question about what is in series. We're going to cover that here very shortly. So if you wouldn't mind, be a little bit patient, and you'll see what I mean here. And I'll cut to the camera here in a little bit and kind of give you an idea of what a series measurement would be, or at least I'll try with the one arm that I have. We'll see. Or I might be able to bring up a picture of how that is done as well. Okay, here we go. So which of the following battery types is not rechargeable? And I kind of mentioned one of these before. The nickel cadmium or NiCad batteries are rechargeable, as are the lead acid and the lithium ion. So your correct answer on this is B, your carbon zinc batteries. These were the common batteries that you got with all your toys at Christmas time, way back when, before NiCads came out and all these other fancy battery types. And they were not rechargeable, and you had to throw them away, and your toy broke down, and your mom, dad, I need batteries. So carbon zinc are non-rechargeable batteries. And you won't find any in the handhelds shipped because the handhelds are typically rechargeable batteries. All right. How much voltage does a mobile transceiver typically require? And you got to just think, what is the voltage in your car? You got a radio, you're going to hook it up in your car, and it's going to take the power from the car. So typically your answer is A or 12 volts. And that's what most transceivers, mobiles, even handhelds, and some of the worldwide HF stations will run on 12 volts. Um, it's like my little 706 over here. It is a 12-volt radio. I have it hooked up to a power supply. I have a 35 amp power supply here in the shack, and that 35 amp power supply runs quite a few things in here, and the 706 is one of them. But one of the things I can do is I can unplug the Anderson connector and disconnect the antenna from in here, and I can take that radio and put it in my car or put it in my truck and just plug in the Anderson connector to the 12-volt supply on my vehicle and add a few antennas, and I'm off and running. Where should the negative return connection of a mobile transceiver's power cable be connected? I kind of mentioned this the other day, um, about how I connect up my radios in my vehicle. And what it really boils down to, the best way to do this, we were talking about interference, I think, and getting alternator whine and things of that sort. To minimize or eliminate the alternator whine, generally you want to go straight to the battery negative or to the engine block ground strap, but you also want to add those the ferrite coils or beads rather to the power lines so that whatever residual noise from the engine might be there doesn't follow the leads back into the radio. So they really need to be connected to the battery source. What is the name for the flow of electronics in an electric circuit? Okay, we talked about voltage before, voltage being the electromotive force, the EMF, or the power behind the flow of electrons. And the name for the flow of electrons in a circuit is D, current. It's called current, which is measured in amps. We'll have that question here in a little bit. I just want to be repetitive so that we have a better understanding of this. So, when you think of a flow of electrons as the flow of water in a stream, if you get out there in midstream, you will feel the current. And it depends on how fast that current is is running. You can kind of think of that as the voltage. If you were in, let's say, kind of a waterfall area where you have a series, where the water's running downstream quite rapidly and quite heavily, you can feel that current, uh, the force behind it representing the voltage, but the amount of water going by you is the current. Answer D. Okay, well, this one should be fairly easy because I've already alluded to this. Which instrument is used to measure electric current? And remember, I told you that current is measured in amps. So the answer to this would be an ammeter. Answer is D. It's the unit of current. I want to try to keep this as simple as possible. There's a lot more to this than meets the eye, but we're trying to get you past here and get a license. So, how is a simple ammeter connected to a circuit? Remember, we did parallel to measure voltage, and in this case, in order to measure current, we want to be in series with the circuit. We want to know how much electron flow is actually going through the wire. So you're going to hook that in series. And what I'm going to do here real quick, I'm going to bring up something here on the internet and see what we can find. Okay. Zoop. Pull this over and so this is how you would measure voltage. You want to know the voltage across there. This is how you would hook up your voltmeter, and it would tell you how much voltage is across that particular component or how much voltage is across the battery. Conversely, if we wanted to measure the actual current or the amount of electrons going through there, it would be measured in series. So you would disconnect one side of the battery or the power source. You would hook your meter probe to that point, and then it would come to your meter and continue this flow of electrons to the component and complete the circuit basically. So this is telling us how much current is flowing in the circuit, while this is telling us what is the voltage across that component. So I'm hoping that kind of helps you there, John, to understand series a little better and parallel. Good deal. All right. So at any rate, um, that's what we would do. Connect the ammeter in series. Answer is A. And that tells you exactly how to do it. Turn off the power or disconnect the power and put your meter in there. Again, here's another diagram of that that kind of shows that particular methodology that I just showed you. I forgot that that was in the book. This right here is actually measuring the current. The meter is in series with, if you look in series with the circuit. And so when you turn the switch on, you can tell how much current that particular device is drawing. Whereas here again, there's your parallel. It's across and parallel with the lamp to see what the voltage is. That should be in your book a little bit. And the bottom one kind of gives you a representation of what a parallel circuit with current branches actually is. And that should be a little bit helpful right there to you as well. Okay, electrical current is measured in which of the following units? Well, we pretty much covered this already. Remember, the EMF or the voltage is measured in volts, and your current or amperage is measured in amperes. So the flow of electrons in a conductor is called current, and current is measured in amperes, and you use an ammeter to measure an ammeter in series to measure how many amperes are going through that circuit. All right, here is something that's interesting. So, which of the following is a good electrical conductor? In other words, which of these actually conducts your electron flow as efficiently as possible? When you look at glass, you can't really think that glass is going to conduct very well. Wood isn't going to conduct very well, maybe if it's wet. Uh, and rubber is definitely an insulator of some sort. So your correct answer here is C, copper. Most of your electrical wiring is copper anyway. You might have some aluminum wiring, but copper is a good conductor of electrical flow, electron flow. What is the name for a current that reverses direction on a regular basis? Now, we've been kind of talking a little bit about direct current at this point, and direct current only flows in one direction. But the other type of current is an alternating current, and it vacillates back and forth. You can think of RF as kind of an alternating signal as well. But for the all intents and purposes, it reverses direction and goes forward and reverses and goes forward. And when you think about your electrical system in your house, it does this 60 times per second. You kind of wonder why the filaments burn out in your light bulbs so often. Not only do filaments in your light bulbs have to endure the sudden impact when you turn that switch on of electrical current starting to flow through it, it starts to alternate 60 times per second. So just imagine what happens over time with that filament vibrating like that 60 times per second. And you don't see it, you don't know it, but that's what's happening. I did a little experiment one time, and because I had an electronic repair shop, and I tell you, I was always replacing bulbs, light bulbs in my overhead light that I would use. It was a swing arm light, and I got so tired of replacing light bulbs every month and a half to 2 months. I decided to cut the wire, and I put a full wave rectifier. Now, what a full wave rectifier does is it actually changes that alternating current into a direct current. It's the same amount of voltage that I had going to the light. It still would light the light, but what it did was it stopped vibrating my filament in my light bulb. And I dated the day I did that. And it finally burned out one day. And when I pulled it out and I looked at the date, it was about 1 week shy of 2 years. So so there you go. Uh, Alternating current definitely will wear out your light bulbs a lot quicker, but direct current right now in my shack here, of course, I had cheap light bulbs. Right here in my shack, I have a light above me that is actually direct current. It's been modified for direct current. So I can't use anything like a fluorescent light. I might could use an LED if it was, the in the right polarity, but I don't know that that'll actually work. But it's just a regular old light bulb, and it's been in here, oh, I guess well over a year so far, and I haven't had to replace it. Meanwhile, other lights in my house I've had to replace because of that alternating current. So, at any rate, that's the name of current that reverses direction, alternating, or AC is the abbreviation. So, why should wiring between the power source and radio be heavy gauge wire and kept as short as possible? So, you need to keep your wiring between the power source and radio to be heavy gauge wire and kept as short as possible. Well, you can look at all these and you might think all these choices are correct, but they're not really. But really, it actually is answer is A, to avoid your voltage falling below that needed for proper operation. If your gauge of wire is too small, you have a 100-watt transceiver that you're transmitting with. As soon as you key that microphone and start transmitting, it's going to start drawing more current, and the voltage is going to stay the same, but it's going to start drawing more current. And the more current you have flowing through your wiring, there is a certain amount of resistance in that wire, and if it's too small, it will begin to heat up, and it could actually cause a fire. And so there is amount of resistance in it, and this resistance will cause the voltage to drop proportionally through the wire. As that wire heats up, the voltage will drop. It'll heat up, and you will not have a fun time with that. We're going to get into Ohm's law here at another time, a little bit later, and that'll give you a little bit more idea of the relationship between resistance and voltage and current. Okay. So, what must be considered to determine the minimum current capacity needed for a transceiver power supply? So, what is the consideration that you need to be mindful of? The efficiency of the transmitter at full output, that is an important aspect. You want to make sure that you can drive your transmitter to full output, which means it's going to draw more power as needed in order to do that. Also, the receiver and control circuit power and the power supply regulation and heat dissipation, those are all things that needs to be considered in all these, and getting the amount of current and voltage you need for your radio and for your shack in general. Like I say, I have a 35 amp power supply here, and my radio doesn't use all that. It might use, I think it uses about 15 to 20 amps when I key up when it transmits. Um, some radios, like a 4-watt CB, is only going to draw maybe about 4 amps, if that, 2 amps or whatever. It's not really going to draw a whole lot of power. So, but there's a voltage regulator in your power supply that is in there, and it keeps the voltage within the limits when it's under maximum load. So your voltage regulator keeps things kind of consistent. So you'll also need to consider how much heat your power supply can dissipate. When you have a power supply, typically they're quite heavy. I do not advocate switching power supplies in a ham shack. A lot of people love them, a lot of people use them. I do not. I do not want a switching power supply. Eh, it's me. But I think switching power supplies can cause more problems uh, than you need to be concerned with. But I have a big heat sink on the back of my power supplies, so it dissipates the heat quite readily. And there can be a significant amount, especially if it is a linear power supply. So the efficiency of your transmitter also figures into the entire power supply scenario. So is it enough to, it is not enough to just know that. So all these things need to be taken consideration. Efficiency of the transmitter, the receiver and control circuit power, and the power supply regulation and heat dissipation. I wouldn't recommend anything less than a 30 amp supply for anybody's shack. Which of the following devices or circuits changes an alternating current into varying a direct current signal? Now, I kind of touched on this again about my little story with my light and everything. And I used a full wave bridge rectifier. So it is a rectifier. Rectifier is really nothing than a DC or a diode. It actually um, current can only flow in one direction in a diode. And I'm going to go ahead and bring up a rectifier here. All right, that is what is a full wave bridge rectifier. That's what that's called. And what that does, these diodes, there's 4 diodes in that are configured in such a way that when AC is entered in at these 2 points here and here, it only directs that part of the alternating current to be the positive part, to go to a DC positive output, and there's a DC negative output as well. So you have a direct current that flows through there. Just a minute. Of course, I have all kinds of nifty little things here in the shack. And I'm going to go ahead and stop sharing for a minute. And I'm going to kind of hold that up. That is a full wave bridge rectifier. And as I look at it here, there's some symbols on it. Okay. It kind of shows, let's see, this isn't focusing very well. All right. But at any rate, this is your positive. It has a positive terminal right here. This is where one of the alternating connections go, the alternating current connections go. And so the opposite side of this, your DC output, they're opposite sides. So AC goes here, and this is the DC. One's negative and one's positive. And it's made up of 4 little diodes in there. So each one of these is 4 rectifiers. Oh, where am I? Come back, little Sheba. Here we go. Back to that. Remember that other diagram that the electronic symbols that I had. Oops. Bring that over. And you can see that right here, again, there's your diodes. There's a full wave bridge rectifier. This is kind of like if you just kind of think back to what I just showed you as far as an actual component, shows that connection as well. And it's another name is a diode or a rectifier. Let's see. Do I have one of those? I can, give me just a minute here. Um, okay, I do. Okay, good. That's what a diode looks like right there in real life. Those are all diodes right there, or rectifiers. They rectify AC and change it into DC or a pulsing DC. What is the name for a current that flows only in one direction? Should be a fairly easy one. And if you answered B, that is correct. It's a direct current. It flows in one direction. It's going in that one direct uh, field right there. It's going there that way. It's a one way circuit, direct current. So batteries are they generate direct current, or they supply. I shouldn't say they actually generate. They actually supply direct current. Even though a current may vary in value, if it always flows in the same direction, it is direct current or DC. What electronic component allows current to flow in only one direction? Now, again, we've talked about the two different names for this, the rectifier and the diode, or the diode, a process of changing AC to pulsating DC. That's important to understand. If you do not use a full wave bridge rectifier, um, if you use a single diode, you're actually getting a pulsating DC. Um, let me bring up another diagram here that hopefully that will help. Um, okay. Here we go. I'm going to bring this over, kind of give you an idea here. If you see this, okay, this is an AC circuit. This is not really an accurate representation. I don't want to use that. Let's see. Here we go. This is what I want. Oh man, you can even see that. That bites. Ah, find the right one here. Mm. All right. When we look at this, don't look at the right side. If you have a single diode that you're implementing in an AC circuit to get a pulsating DC, all you're going to get are these positive peaks. You're not going to have this part at the bottom. Uh, Over here on the right side, it says it's a rectified pulsating DC current. Eh, it, it's not as simple as that. There's actually a space in there on that. Um, and I think they kind of misrepresented this. There is a way you can get this, I believe. Oh, geez. But if you had a full wave bridge rectifier, it would be a straight DC, a straight line pretty much. It wouldn't be pulsating. Let's put it that way. Did I confuse everybody? Okay, any rate, let's get on with this lesson here. So what are the names of the two electrodes of a diode? Okay. Now, if you've looked in the book, it'll tell you which side is which side is which, and there's two sides to it. One is an anode and the other side is a cathode. But when you first take a look at the symbol for a diode, the cathode side is represented by the short straight line at the tip of the arrow, and the anode is represented by the arrow itself. Kind of follow that? Okay. Your answer is C on that. So how is the cathode lead of a semiconductor diode often marked on the package? And when you look at a diode itself, it's just a very basic designation. It's usually with a stripe. That is your cathode side. That's the side that has the little line at the which would be represented at the end of the little arrow that's pointing into the line. That's your cathode side, and the opposite side would be anode. So, and it's important to know that so that you know which side to actually hook your DC or AC or your DC negative or DC positive side to. So, not having much room to put a letter, a little tiny stripe does this quite nicely. Okay, the next component we're going to talk about is what electrical component opposes the flow of current in a DC circuit. Do, 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 do. Where is that? Oh, I can't find it. At any rate, there was a little picture I was going to show. Uh, the component that opposes the flow of current in a DC circuit is called a resistor. Join the resistance. Join the resistance. Let's see if I can find it here. There it is. Join the resistance. Om, om, om. And I love that little cartoon. It shows a resistor and all these bald-headed guys doing their little ohm thing, and that's what a resistor does. It opposes the flow, or it actually kind of almost regulates in a way the flow of current in your circuit. Just like a beaver dam may resist the current flow in a stream, that's what a resistor does. And it's measured in ohms. We're going to learn that as well. So, what instrument is used to measure resistance? Um, Again, the term we use for resistance, as far as what the value of a resistor happens to be, is an ohm, OHM. So it would stand to reason that in order to measure that, you would use an ohm meter. Again, your multimeter has that function on there. You want to know what the resistance of a particular resistor happens to be. All you would do is turn your dial to measure resistance, and it would give you a readout of what the ohm value of a resistor would be. So the unit of resistance in a DC circuit is the ohm. Now we get into another type. What type of component is often used as an adjustable volume control? Not many people have used this term, but it's a simple what's called a potentiometer. And ham operators are about the last to enjoy the potentiometer. This is found in the volume control of most handheld ham radios and ham sets. We usually have the beloved potentiometer. So that's what your volume control is a potentiometer. It's, if you have an actual knob that you turn. I know we're all used to sitting in front of our TV, and we have little buttons on our remote control to lower and increase the volume on our TVs. And let me see here. Dave has a potentiometer there. Let me stop sharing here. I don't know if anybody can see that or not. Back it up from your camera a little bit there. That's your potentiometer right there. Everybody see that? Yeah. Thank you, Dave. So there we go. All right, potentiometer. It's an adjustable control or basically adjustable resistor. What electrical parameter is controlled by a potentiometer? Well, I pretty much gave you that answer just a moment ago. It's the resistance. So a potentiometer varies the resistance in most ham radio volume control circuits. It's a variable resistor. Answer is B. Which of the following is a good electrical insulator? You're doing great there, John. Which of the following is a good electrical insulator? Now we're trying to insulate to keep electron flow from going someplace. And when you look at these, mercury is used sometimes in your switches, your thermostat switches, that when the little spring in there gets to a certain point, there's a little tube that has mercury in it. Mercury does conduct electricity, and once that little tube gets to a certain point, the mercury flows to the other end, and it makes contact with two metal probes, turns on your furnace or air conditioner or whatever. But so in this case, though, your insulator is glass, and they might have a multicolored glass power pole insulator. I have one of those, but it's out in my garden right now. I don't have it in here. I keep meaning to bring it in. It's been sitting in my garden for years and years, but I have one of those insulators. John, you may have seen them or somewhere around. Yeah, you know what they are. Good deal. So what type of electrical component stores energy in a magnetic field? Okay, this is a little bit different. We're getting into some other stuff here. And there's a magnetic field that is created in this component when uh, when it has electricity applied to it, and it's called an inductor. It is the coil called an inductor that stores energy in the magnetic field. We can actually see the effects of an inductor with a magnetic compass. Your answer is C. I want to know what it says in the book here. I'm going to look at it real quick. And we're looking at T6A06. I think it might even have a picture. Let's see. There it is. Yeah, if you look at the picture, it's actually, I think, in the next one, T6A07, is the inductor. You can see that little coil there in the picture under T6A07. That's kind of what an inductor might look like in the open anyway. So it's a coil of wire, and answer is D for this one. So what is the ability to store energy in a magnetic field called? Well, if it's an inductor, then it would stand to reason that it's called inductance. And when exposed to current, coils will develop a magnetic field, which can be detected by holding a magnetic compass near the energized coil. So, energy stored in a magnetic field is called inductance. Okay, we got to remember that because we're going to get into capacitance here pretty soon, which does a similar thing. So, the basic unit of inductance, however, is a little bit different. It's actually measured in henries, but um, most of the time it's usually millihenries, microhenries, or millihenries rather. But the basic unit of inductance is called the Henry. And like I said, because it is a fairly large unit, it's usually measured in 1/1000th of a Henry, Henry or a millihenry or 1/millionth of a Henry, which would be a microhenry. That's your unit of inductance. Okay, we're talking about impedance. Okay. Now the resistor is kind of it impedes the flow. Yes, it does. Um, but impedance really is pretty much the opposition to AC current flow in a circuit. Resistance is the opposition of DC flow in a circuit. Impedance is the opposition of AC current flow in a circuit. And it's a very important concept to understand in radio. It is the composite opposition to the flow of current in an AC or radio frequency circuit. So we need to take impedance into account uh, in these instances. Okay, so what is the unit of impedance? Well, it's kind of like a resistor. It's ohm. I don't want to get too confusing here, but it's represented by the letter Z. If you see the letter Z, we're talking about impedance. If you see the letter R, we're talking about resistance, but it's the ohmic resistance that opposes current flow within an alternating current circuit. So there's a delineation between how resistance is viewed in a DC circuit versus impedance in an AC circuit. Um, and even though it's a complex number, it does again follow Ohm's law very much like the DC does, and that's kind of a good thing. It's just as resistance, it is the ohm. Answer is D. The ability to store energy in an electric field is called. Okay. Now, we're talking about something different here. We're storing energy in an electric field, and it's called capacitance. Capacitors store energy in an electric field. This is called capacitance. There is a difference between inductance and capacitance, by the way. And once we understand that, the basic unit of capacitance is the farad. Now, again, the farad is kind of a large value, um, and it is usually measured in micro or picofarads. Like the inductance is measured in henries, capacitance is measured in farads. So, what is the electrical component that stores energy in an electrical field or an electric field? Well, capacitance is what we were talking about, so it would stand to reason that it's a capacitor. Um, the electric field has capacitance, which is stored in a capacitor. Um, Back when I was doing repair on telephones, inside the older telephones, there was a circuit which had a specialized capacitor in it. And when a phone rings, there's like, quite a bit of significant energy that goes into ringing your phone. And what I would sometimes do is I wasn't the only one that did this, but we would take these capacitors and I'd charge them up and I'd lay them on the counter. And if one of the guys was happened to pick it up and crossed his finger across the two leads on a capacitor, he'd get a little bit of a shock because there was stored energy in that capacitor. So yeah, maybe it's not funny, but to me it does. And I think back to my days when I taught electronics and did repair and stuff like that. That was just one of the little things we used to do. It wasn't a harmful thing. It just give you a quick shock, much like when you would get a shock rubbing your feet across a carpet and you get that static electricity shock. That was pretty much the kind of shock you would get from one of those capacitors out of a telephone. So what type of electrical component consists of two or more conductive surfaces separated by an insulator? Okay, we were just talking about capacitance. So the component that stands to reason would be called a capacitor. It has two conductive surfaces separated by an insulation. I don't know if it actually shows that in here or not. Yeah, on page 147, we see a diagram there that illustrates what a capacitor looks like or represented internally. You got your two plates with leads, and there's some type of dielectric in the middle. It can be paper, it can be air, it could be, some other type of insulating material. And it's used as a filter basically in some components and oscillator circuits and things of that sort. So it's two or more conductive surfaces separated by an insulator. That's what your capacitor is. What electrical component is used to connect or disconnect electrical circuits? An electrical component used to connect or disconnect electrical circuits. This one should be fairly easy. If you want to connect, yeah, and if you answered B, that's right, it would be a switch. Flip it on, the light comes on. Push the button, the radio comes on. Push it again, flip it again, it all goes off. So yeah, a switch is that electrical component. It is represented by, let's see, I think I have it in here somewhere. Well, I thought I had it in here. That's a relay. Oh, here we go. These are switches right here. Okay. So it's a single pole, single throw, single pole, double throw, various types of switches. If you flip it in one direction, like in this instance, we're talking about a single pole, single throw. Flip the switch, make this connection across here, flip the switch again, you break that connection. Okay, what electrical component is used to protect other circuit components from current overloads? Oh, here we go. Now we're getting into simple little basics of circuit protection, and it's called a fuse. And of course, fuses are rated. If you look in your little fuse box under the dash of the car, you'll see little numbers on there. They can be 3 or 5 or 10 or 20 or whatever. That's the amperage. That's the amount of current that is allowed to flow through that circuit without damaging anything. So if you have something bad in your car that's drawing more current than it should, then that fuse is going to blow. Or even if you short something across the wires, that fuse is going to blow and you're going to have to replace it. Basic automotive electronics. Okay, which of these components can be used as an electronic switch or amplifier? This again is getting into other territory. It's a very interesting territory. I've always liked this particular component personally because there are so many different types of these little transistors. Um, they do a variety of things. They're capable of amplification. They can also act like an on and off switch. You can set up oscillator circuits and things of that sort. Transistors are used in the output to amplify your signal in the output of your radio. And there's just a lot of different types of transistors out there for various purposes, but it can be basically used as an electronic switch or an amplifier. So, what class of electronic components uses a voltage or current signal to control current flow? And again, we're talking about that same little um, component that we just talked about, and it would be a transistor. How that operates, let's see if I can bring up my. I'm going to bring this up here, bring it over. There we go. This is a transistor, and what happens is that there are several uh, leads or three leads off of them, generally speaking, depending on whether it's an NPN or a PNP, and they're uh, the electron flow is going to go through these leads. The base itself, you have a collector and an emitter, and depending on how voltage or current is applied to the base depends on what this transistor is actually going to do, whether it's going to conduct or whether it's going to turn off. And let's see. Let's see if there's something else different here to kind of give you a little bit better understanding, but I don't know. I'll leave that up for now over here on the other page. But transistors are a replacement for tubes. Um, Tubes had many functions as well, and a lot of things, transistors have been employed to replace the tubes these days. And in many cases, the integrated circuit is a collection of many, 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 many transistors contained within a integrated circuit. And small amounts of voltage or current signal can control large amounts of current flow to other circuits. Okay, which of the following electronic components can amplify signals? Again, we're talking about that little component called a transistor. If you answered A, that is correct. It acts as a switch and can also amplify signals. What is the term that describes a device's ability to amplify a signal? Um, Now we're talking a little bit about another way there or another aspect that when you have a signal, you want to amplify it. The word that we use is gain. It'll take a weak signal and make that weak signal stronger. We talked about amplifiers the other day, the RF amplifiers, and I have one here, 15 watts in, 85 watts output. So if I put 15 watts into that linear amplifier, it's an RF amplifier, there's a certain amount of gain that it has to pump out, make that signal go from 15 watts to 85 watts. So that is what we mean by gain. Amplifies a weak signal and makes it stronger. So which of the following can be the primary gain-producing component in an RF power amplifier? Again, it's that nice little component called a transistor. It uses some power gain, and it helps. It also draws more current. Hence NFL. What? This thing actually goes. Okay, not sure what that is, but at any rate, the transistor again is that gain-producing component. So which of the following components can consist of 3 layers of semiconductor material? And again, we're talking about the transistor, B. It is a fundamental solid-state amplifier. It's a 3-layer bipolar transistor coming in 2 flavors. I mentioned this before, the NPN and PNP, where N is a negatively doped semiconductor material and P is a positively doped semiconductor material. And as far as that is concerned, it kind of determines your electron flow and how it gets amplified, how it's used as a switch, and things of that nature. So what does the abbreviation FET stand for? Now we're getting into a little bit of a different transistor. It's used for different purposes, but it's called a field effect transistor. And they accomplish many functions within your equipment. They provide voltage amplification, for one thing, where small changes in the gate voltage can result in large changes in current flow, leading to voltage amplification. And one thing about the FET is that, in that it's different from the standard transistor. Let me see if I can find it here. Up, 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 up. Oh, here we go. Here we go. Transistors here. Okay. In a standard transistor, you have a base, a collector, and an emitter. And this is an NPN, meaning NPN. Your emitter is a negatively doped material. Your collector is a negatively doped material, and your base is a positively doped material. Conversely, the PNT or PNP is a little bit different. And then when you get into FET transistors, which is represented here, they're named a little bit differently. You got a drain, a source, and a gate. And a gate functions pretty much like it says. It determines how the drain and source are going to function and amplify and control voltage. All right, any questions here? Because we are at the end of this topic, and the next one we're going to talk about is Ohm's law. We're not going to get into that tonight, but that will be next week. So, anybody have anything they want to talk about? Anything they need clarification on? Some of these. Oops, sorry about that. Some of these diagrams. I got to mute you. Okay, I have uploaded to the Dropbox. If you don't have that link, let me know. But they are some of that stuff is up there. I'll put more stuff as time permits, and to give you a little bit of helping hand here. All right, John, go ahead. I'm going to unmute your mic.
This really doesn't have to do with what we need to know, I guess, but what I don't understand about alternating current, if it's constantly changing the direction, how's it ever go anywhere?
It doesn't. The aspect of alternating current is that it actually goes from a negative or from a positive to a negative. And there is a vibration that goes on, yes. Alternating current is just one of those strange animals, and I don't want to get too technical with it. Probably in lay terms, the best thing to understand is that there's a positive and a negative. So when that signal is sent down, it's just how they transmit the current to your households, uh, and how it's set up. A generator does an alternating thing as well. It generates your positive. It has a positive aspect to it, and then has a negative aspect to it. And this is how, when I was describing the full wave bridge rectifier, um, it alternates that way, not so much back and forth, although there is a vibration, like I said. In the full wave bridge rectifier, you connect that AC to certain 2 points. Where is it here? I can't raise my arm up, so I have to stand up. When the alternating current is connected to the 2 points, at one point, that one side of the alternating current here going into one side is a positive, and on the other side, it's a negative. I'm being a little simplified here. And when it's positive, okay, it feeds out on the positive side. When it goes negative, it goes to the negative side of the rectifier. And that's what turns it into a direct current feed, changes AC to DC. So I kind of want to make this as simplified as possible. If you, let's see, let me go over here to this other site. Okay. Let me give you some information here. I'll put this up. This little article in Wikipedia can give you quite a bit of information. I've looked at this before, and it kind of gives you a little bit better aspect. If you really want to get too deep into it, it will actually get into the depths of alternating current, why it exists, the different phases, whether it be 3-phase, 2-phase, single phase, whatever, and the frequencies that are used. It has a lot of information there. If you want that, I'm going to go ahead and copy that into the chat window, and you can kind of copy and paste there if you want. But that should help you quite a bit, I hope, in understanding AC. But
I was gonna interject here that it's not that the voltage or the it's not changing direction in the wire.
Right.
It's as a function of time, so it's going from positive to negative, back up to positive. That's what's alternating. It's still going down the wire.
Yeah.
Okay. So that's, you know, in respect to how you asked it, how does it get anywhere? What we're doing is we're changing the polarity of it over time.
And it does that 60 times per second.
Over time.
Yeah, it does it 60 times per second. And if you think about the vibration that's in in the filament of a light bulb, it vibrates because it is changing not direction, but it's changing polarity. And think of it as a kind of a knee-jerk reaction, for lack of a better term here, that when it flows, when that flows, the current flows in one direction or goes positive in one direction, the filament tends to flex in one direction. And when it reverses or when it goes negative, it knee jerks into a different direction. And it does that 60 times per second. So, yeah, it really, like Dave was saying, it doesn't alternate back and forth. Rather, it alternates between negative and positive. Good deal? All right. Anything else we want to talk about? John?
No, actually, I've had some of these conversations with Herb before,
Okay.
and he's explained some of these things that, maybe I understood at a certain level, but it got better tonight. Actually, things started to click.
Okay.
So appreciate it.
That's good. Yeah, I didn't share the screen when I brought up that Wikipedia site, but it's in the chat box. Take a look at that. I mean, you really don't have to get that in depth. This is kind of stuff that you might want to know if you're going for your extra class license, or going for something in the commercial field, and you get a little bit better understanding. That is covered a little bit more in depth in the extra class, but for the purposes of the tech class, um, you just want to keep it as simple and basic as possible. So, anything else from anybody? Tom, do you have anything? Is Tom there?
Yeah.
There he is. We don't see you, Tom.
I'm on the phone, Wayne. I'll have to get back to you.
All right, no problem. All right, anything more from you, Dave?
No, I'm fine.
All righty. Well, if that's it, I'm going to go ahead and we'll close out for tonight. And Monday, let's see, this is Thursday. Monday, we'll be picking back up on Ohm's law. And with Ohm's law, it'll give you a little bit indication of the relationship between voltage, inductance, reactance, current, all of that, and how you would actually calculate. We're going to get into some mathematics, some formulas. It's nothing really difficult. We'll also get into, I think, maybe a little bit of the power formulas as well. But this is probably enough for tonight. There's a lot that we covered here as far as electronics are concerned, and I hope that everybody got something out of it that is meaningful. And just drop me an email if you have questions or anything that you need answered, and I'll do my best to answer them. So I'm going to go ahead and stop the broadcast, and then we'll go ahead and end this.